Every material has a hidden story that only reveals itself when exposed to heat. Thermogravimetric Analysis, or TGA, is the tool that lets us uncover that story. Whether we're working in materials science, pharmaceuticals, or manufacturing, TGA helps us see what's happening behind the scenes, how a material transforms, breaks down, or reacts as temperature rises. In this presentation, we'll explore how TGA works and why it has become such a powerful technique across modern industries. To understand TGA, imagine placing a tiny piece of material on an ultra-sensitive balance inside a furnace. As the temperature increases, this balance records every small change in weight: a loss of moisture, a chemical reaction, decomposition. The instrument captures it all. TGA combines heating, precise weighing, and data interpretation into a single seamless process that reveals the material's behavior under thermal stress. So why does TGA matter? Because the changes that materials undergo when heated aren't always visible to the eye, but they're crucial for real-world performance. TGA lets us monitor these changes in real time. We can detect moisture loss, track decomposition, measure oxidation resistance, identify residual solvents, and even observe phase conversions. Each mass change acts like a plot twist in the material's thermal journey. These insights drive key decisions in product development, quality control, and industrial processing. The principle behind TGA is surprisingly simple. When a material is heated, it undergoes physical or chemical transitions, and these transitions cause measurable changes in mass. The instrument's microbalance can detect weight changes as tiny as 1/10 of a microgram. This extreme precision allows scientists to study even subtle thermal events that would otherwise go unnoticed. TGA translates these microscopic transitions into clear, meaningful data. A TGA instrument is built around 3 core components. First, a furnace that heats the sample, sometimes up to 1,000 degrees Celsius or more. Second, a microbalance that continuously measures weight changes with remarkable accuracy. And third, a gas flow system, which introduces inert gases like nitrogen or reactive gases like air or oxygen. Gas flow matters because a material can behave completely differently depending on the atmosphere. For example, a polymer may decompose under nitrogen but burn in oxygen. TGA gives us the ability to study these transformations across multiple environments. TGA isn't just one type of experiment. It includes several methods depending on the analytical goal. Direct TGA steadily increases temperature over time and is ideal for studying decomposition, moisture loss, and thermal stability. Isothermal TGA holds the temperature constant, so we can observe slow reactions like oxidation or evaporation behavior. Stepwise or modulated TGA alternates between heating and holding periods, making it incredibly useful for separating overlapping thermal events in complex materials such as polymers. Each method offers unique insights into how materials behave with heat. A TGA curve is essentially a thermal fingerprint. Every slope, plateau, or drop corresponds to a specific chemical or physical event. We can identify moisture content, both free and bound. We determine thermal stability, the temperatures where the material begins to change. We can break down the composition of a sample by observing filler content or inorganic residues. And we can map out decomposition steps and reaction pathways. All of this information allows scientists to understand how a material behaves throughout its thermal life. TGA has become a standard tool across industries because it answers real, practical questions. In polymers and plastics, it helps determine degradation limits, additive content, and safe processing temperatures. In pharmaceuticals, it reveals solvent and moisture content, supports stability studies, and helps analyse degradation pathways, often alongside DSC. In battery and energy materials, it's essential for studying decomposition, carbon content, and thermal runaway behaviour. In chemical manufacturing, it supports quality control, oxidation studies, and catalyst evaluations. Even food and agriculture rely on TGA for moisture and ash content analysis. Any industry concerned with thermal behaviour depends on TGA. Let's look at a few practical examples. In polymers, a small weight loss at low temperature could indicate moisture, while a larger loss at mid-temperature may reveal plasticizers. And full decomposition at higher temperatures defines the material's thermal limit. In pharmaceuticals, an 8% mass loss below 100 degrees Celsius indicates bound water, a critical factor for shelf life and packaging. In battery materials, a mass gain under air may signal oxidation, a key parameter for lithium-ion safety. Each TGA curve solves a real industrial challenge by providing actionable insights. To summarise, TGA is a technique that uncovers the thermal identity of materials by measuring mass changes as they are heated. Its principle is simple, yet the information it provides is incredibly powerful. We explored the instrument components, the various TGA methods, and what a TGA curve can reveal. We also looked at how TGA is applied across industries, from polymers to pharmaceuticals, batteries, chemicals, and even food sciences. Ultimately, TGA helps scientists and engineers understand how materials behave, degrade, and transform, giving them confidence in design, production, and quality control. Thank you for watching, and remember, every material has a thermal story, and TGA is how we read it.